confused and lost. But based on my experience on the fourth lecture, it's a little bit more clear for them what they do or why we do these steps, and hopefully it's the same now for you as well. Because from next week, we will move to the new topic, which is Fourier series. Again, the first lecture is very confusing, but I promise that in the second lecture, it will become much more clear because we do a lot of example on the second lecture. Just, I want to prepare you for next week. Today, we will continue to talk about the linear time invariant systems and how we can check if a linear time invariant system is stable or not stable. And then we will talk about the convolution of two functions, some properties of convolution, and then how we can obtain the Laplace transformation of this convolution. If you remember, last week I introduced linear time invariant system to you. And as it's stated in the title, a system is LTI or linear time invariant if it's linear and time invariant at the same time. What does it mean when we say we have the linear system? Assume you have a system with two different inputs, and of course some operation will happen in the system, which I just used the T notation here, and then we got the two outputs for each input. A system is linear if you combine any linear combination of these two inputs or n number of inputs together, then you will see exactly the same linear combination in the outputs as well. When A and B, A1 and A2 are some constant numbers. Then you have a linear system. A system is time invariant if you implement an input to the system with T0 delay, with T0 shifting, then you see exactly the same amount of delay and shifting in an output as well. Then you have invariant system. And the combination of those is the linear time invariant system. Of course, all of the systems around us are in a time domain and they operate in a time. But when you want to do design a controller for any system, or you want to do or design a filter for any system, we need to have a system in frequency domain as well. So that's why, again, we use Laplace to transfer or move a system from time to frequency domain. When we move to frequency, we need to find something which represents exactly the same input-output behavior in a time we have, in a time domain which we have. The researchers did the work and they found that by using the transfer function of any LTI system, we will have this input-output relationship we want. How we can find the transfer function of any system? If you divide or obtain the Laplace of output and divide it by Laplace of input, then you have the transfer function of the system. And again, from here, the output in frequency can be obtained by multiplying the transfer function with the Laplace of input. Then you have an output in frequency. If you remember, last week I also showed you that you can have the impulse as an input to any system. Then the output you get in time is always h of t, which we call them impulse response of the system. And again, last week I showed you that impulse response can be obtained if you take the inverse Laplace of transfer function. Because assume you have a transfer function, h of s. So if you move from right to left by inverse Laplace, then you have the impulse response of the system. And in a very, very general case, for any LTI system, the transfer function can be obtained by this one, this formula. And if you remember, last week I explained to you that here usually the student making mistakes that we know it's the Laplace of output over input. But mathematically, I prove to you when we want to do it, the coefficient of y of s should always come in the denominator, and the coefficient of x of, it should be s here, sorry. I tried to modify this, it's in a frequency domain. The coefficient of x should come here at the top. Then you have a transfer function of any LTI system. You can use transfer function of a system and obtain the poles and zeros of the system. What are the poles? Based on the definition, the poles are the values of s which make this transfer function infinity. Which again, if you put the denominator equals to 0 and use Maple to solve it for you, for instance, then you have the poles of the system. And in order to obtain the zeros, we put the numerator equals to 0. Why? Because we are looking for the values of s which make this transfer function equals to 0. Now we will do some examples, which we will do it, first you will do it alone in 5 to 7 minutes, and then we solve them here together. So the first one, we have this differential equation which is for an LTI system. So this differential equation is given to you. First you need to obtain or determine the transfer function of the system, and then find the poles and zeros of the system. I think 5 minutes should be enough. So you have 5 minutes to try yourself first, and then we do it together.
Ja, og så isolere ud bagefter, og så ud fra det kan vi dividere over, så vi får på. Så det så problemet er, den tid hun har sat af, den tid det tager for at skrive på.
And you know the solution is in the next slide, but please don't look at it.
Det er jo
Altså, ja, men
når det ikke står, der skulle man bare gå ud fra, at det var noget plan. Så ja, det er S, ja. Og så bare S, og så minus ja, hvis det er 1.
Koefficienten er x øverst, eller hvad?
Jeg tror måske, jeg er i gang med noget klogt. Men vi skulle aldrig jo.
Det var ikke så meget. Så den bliver bare sådan
Og det er for faktuelt. Ja, ja, også. Ja, og så kan du selvfølgelig dividere med x, så du får udsluttet. Hvordan har I S i anden? Plus S. Hvordan?
Nå, fordi hvis det er S i anden, og hvis det er 0, Det bliver SU til det. Og så er det bare godt.
SU.
Og så får minus 2.
Minus 3 S2 plus 2. Det er virkelig omvendt.
Så sætter man den her minus 2.
Og jeg vil fakturere det først.
Faktorisere det?
Ja.
Oppe i opstilleren?
Nej, dine andengradspolynomier. Carsten, hvordan du fakturerer?
Nej, jeg tror faktisk, jeg vil gøre sådan her. Så siger...
Det er bare fordi, jeg tror, jeg har noget her.
Jo, det er du nok nødt til, fordi du er nødt til at kun have en.
Jeg fik det til 1 over 1. Smart. Men jeg tror, det giver S minus 2 og så S plus 3. Det er mit bud.
S plus 2 og minus 3?
Nej, omvendt.
Altså, jo minus.
S minus 2, S plus 3. Giver det det? Lærkogt. Lærkogt. Minus 2. Men giver det, er det ikke plus S?
Du har en 0-punkt, der hedder 2, og så har du...
Nå, nej, undskyld, nej, jeg er i gang med faktorisering af det.
Så kan det ikke være på lidt se, hvis du må gøre sådan her. Så du
Du skal jo ikke lade plads transformere den der HRS.
Vi tager et startmål med det her. Plus minus 6. Det er det, jeg tænker på.
Jeg fik S til minus 3, ja.
Altså egentlig som pol.
For pol, ja. Og den anden, så må det...
2 og minus 3. Og så er det 0 punkt også 2.
Okay.
Ja.
Do you want a few more minutes or?
Det er fordi, jeg kom til at...
Let's solve it
Jeg er
together.
faktisk ikke, om man kan det.
Few more minutes.
Few more minutes. Okay, cool.
Nu trækker de over dig for
Maybe 3 more minutes.
Jeg ved ikke, om det er fordi, jeg tror, jeg får kortet brød.
Det kan være, jeg har ikke.
Jeg har bare gjort det der. Så der er kun én næste.
Det er ikke noget. Jeg holdt det bare.
Det finder vi ud af, hvor forkert eller rigtigt man er slået. Har du fået nogen nuller så? Og det er minus 2 så? Plus 2. Ja, det giver, ja, i den første må det jo så være. Det kan godt være, at jeg har overkompliceret det. Jeg har...
Hvorfor gør du det? Hvorfor gør du det? Altså, plus derovre, så er det rigtigt.
Jeg har virkelig lyst til at se det.
Jeg har den her. Hvad mangler du at finde?
Jeg ved ikke, hvad jeg har lavet.
Hvad fik du på? Hvad fik du på til dig?
Jeg fik Polen til minus 2.
Det gør jeg også.
Og zeros. Men det er så, hvis jeg går til mit tidligere resultat, jeg får til 2.
Jeg får den der, ikke?
Ja, det er også den, jeg har lavet.
2 og S plus 2 plus S plus 3, som er den der delt op, ikke?
Ja. Det er også det, jeg gjorde. Og så, jeg ved ikke, om man kan det, men så fjerner jeg bare det der. Så
Ja, de går ud med hinanden.
Ja.
Så står der S plus 3 tilbage, for at det giver 0.
Ja.
Den der skal jo så give 0, ikke? Så må det være minus 3.
Men jeg tænker bare zeros, den har man jo så fjernet. Men jeg ved ikke, om man så bare kan gå bage dertil, og så gøre den til noget.
Det er 2 fra udgangspunktet med den der, ikke? Fordi den der, hvis den giver 0, så skal der være 2.
Er det svar?
2 minus 3. Hold kæft, det er godt.
Jeg prøvede at skrive duvelen frem, så du har det her med I over X. Det giver det der. Og så faktoriseret af anden, som har 2 førstegradspolynomer. Det brugte jeg lige lidt tid på. Og så tænkte jeg, at de der 2 kan jo så gå ud af sådan. Og så fik jeg en nævner, hvor man meget nemt kan sige, at når S er 3, så giver den 0. Så heroppe, det er jo fra starten, der kan man se, at
okay, now let's solve it together. So this differential equation is given, and now we want to find the transfer function. So we want to find h of s, and based on the definition of transfer function, we need to have the Laplace of output over the Laplace of input. So here, if I take the Laplace, then I can move toward obtaining the transfer function. So as a first step, you need to take the Laplace from both sides of this equality equation. And we have the Laplace of second derivative and first derivative. You can use table 7.3. However, for instance, for here, we have s2y of s plus some initial value term. But what is the initial value here?
0.
0, exactly. Why? Because if you remember, I told you that it is 0. If it's nothing mentioned there, then all are 0. So I don't need to write the rest here. Then for the second one, again we use table. Now here, we have capital Y of s in all term here, so I can make the factorization. And here also I have x of s, so I can make the factorization on the right as well. S2 plus s minus 6 equals to. And now I want to obtain this. So what I do, I multiply it by 1 over x of s. You don't need to do it. You can do it on your head, on your mind if you want, but here I want to show. So. And then y of s over x of s, which is your transfer function, it would be s minus 2 over s2 plus s minus 6. This is the transfer function. We are not 100% done, but I want to do it a little bit wrong and show you one mistake which usually we can make, but I will back and modify it in a few minutes. But for now, this is the transfer function which we obtained, and up till this point it's correct. But let's see. For the next, we want to find the poles and zeros. For the poles, we know that I need to put the denominator equals to 0. So, in order to obtain the poles, I put s2 plus s minus 6 equals to 0. And again, you can use Maple to solve this for you. You have s1 equals to 2 and s2 equals to 3. Am I right?
Minus 3.
Minus 2, yeah. So you have 2 poles, or sometimes we call it P1 and P2. For zeros, I put the numerator equals to 0, and I have 0, 1 at 2. Okay. When you have the poles and zeros of any system, we can plot, I know that I have not asked it here, but we can always plot the pole zero diagram. We call it pole zero diagram. Maple can also do the plot for you, but you can do it manually if you want. And And here we have a complex S-plane. Complex S-plane. And here is the real part of the complex S-plane, and here is the imaginary. So we have two poles at 2 and minus 3. Keep in mind that for pole, when you want to do the plot, the notation we use is always cross. So even if you use MATLAB, Maple, or any other tool which can do this plot for you, you can see that they use cross as well. Now for plotting the zeros, I have another one at 2. We use the circle notation, this empty circle notation. Okay, now you can see that I have a pole and 0 which are at the top of each other here. Actually, if you do this in exercise or exam and you reach to this point, then you should recognize that you missed a step here. So let's be back here. Why? Because this can be written as and you can see this pole and 0 cancel out each other and it will become this. So always and always when you obtain the transfer function, it's necessary that you do the cancellation. If you forget to do this, then maybe you have a plot, and then of course you can recognize, go back and modify it. But always do the cancellation. Then we do the pole and 0 here. Based on this, now I have only one pole, so I don't have this anymore. I have only one pole, P1 and S1. But for zeros, actually the system has no zeros. Why? Because this one cannot become 0 at all. So the system has no zero. And again, we don't need to have this cross or circle here anymore. And that would be the plot of pole and 0. How these poles and zeros can be used? Actually, we use the poles only and only for a stability check of the system. Of course, you have the solution here as well. But now, let's talk about the stability of LTI system. But any question here? Good. Now, how we can say that if a system is stable or not? If you have an LTI system that for all possible bounded input gives you the bounded output, then you have a stable system. Actually, this is a definition which we call it BIBO stability. So BIBO stability, and BIBO comes from bounded input, bounded output. If you look at the literature, we have a lot of definition for stability of a system, and this is one of them. And this BIBO stability says that a LTI system is stable if and only if for all possible bounded input we get bounded output. Now, a question which may come in mind is that what is bounded input? Why we call it bounded? Actually, we call a signal or an input bounded if you plot it, for instance, it is between two specific range of A and B. For instance, unit step is a very good example of bounded input because it's always and always between 0 and 1. So, for all bounded input, if you get bounded output, we have the stable system. Now I have a question here. Do you think that using this definition to check the stability of a system is realistic, is efficient? Can we do that by just using the definition? Any idea?
I guess it would be no.
Yes, actually the answer is no. Why? Because it says for all possible bounded input, we get bounded output. Even if you try 1,000, 1,000,000 times of bounded input and you get bounded output, there is no guarantee that the +1 one which you try gives you the bounded output. So it's not an efficient way or realistic way to check the stability of the system. Then what we do instead? Then we use the poles and the location of the poles in the complex S-plane to check the stability of the system. Because again, the researchers did the work and found that for all stable system, the real part of the poles should be in the left side of the plane. If the real part of your pole, here is a real number, so you have only real part. So if all for all poles, the real part is on the left side of this plane, then you have stable system. As far as one of them jump to the right, then the system becomes unstable. Again, another question which may come in mind is that how about if you have a pole on imaginary axis? Because it's not in the left, it's not in the right. Again, based on which definition of stability we use, some people call it, if the pole is here, we call it marginally stable. And based on some of the definitions, they call it unstable. And if an exam, if you write it as a marginally stable, I accept it. And if you write it also as unstable, I also accept it. But keep in mind that for stability, all poles should be here. For unstable, if one of them is here, that's enough. And here, we call it marginally stable. Any question? Okay. Here I have another example for you. You have around 7 to 10 minutes time to do it. I have 3 different differential equations here, and I want that you check the stability of each. Of course, we do it all here together as well, but now you have, let's say, 10 minutes to do this example.
Oh ja. Det er altid sådan. Det giver mening.
Ja, okay, nu sidder du.
Hvad? Den her, ikke? Ja, min første underopgave i den her opgave. De andre er ikke noget til endnu. Jeg skulle også lige... Jeg skiftede jo papir, så jeg skulle lige skrive lektionen og hvad vi har og så videre. Det var hvad kan jeg
Det der med, at man skal gå rundt.
Jeg lavede ikke nogen to. Eller 2 år kunne man jo egentlig bare sige sig selv med det. Men jeg har sidste men jeg skrev det helt op. Mig og 3 år. Det er dobbeltmærke.
Det er rigtigt.
Hold kæft, du skal have
Ja,
det.
det er godt. Ja, så...
Er det det der Formel 1, der kører videre?
Ja, jeg har det i øret stadig. Nej, det er sådan, jeg kan finde ud af, hvor svært det, jeg laver, er, om jeg kan lytte til noget, mens jeg laver det. Hvis jeg går sådan og laver de her elektroteknikopgaver, så er jeg nødt til at fjerne Formel 1.
Så Gustav?
Ja.
Så det er når realdelen af polerne er større end 0?
Mindre.
Ja, så er det stabilt.
Ja.
Ja.
Så den første er ustabil, den anden er stabil, og den tredje har jeg ikke.
Jamen, hvad så hvis de har en, der både over og under? Er den så stabil også, eller hvad?
Nej, hvis der er bare
Hvis den lå midt på,
Så er en derovre, så er det ustabil.
hvis der er bare en, der kommer over, så bliver den stabil.
og hvis den lå på den imaginære...
Marginalt stabil, sagde hun jo. Hvis den lå på imaginære aksen.
Hvad sagde I, hvis den ligger på imaginært?
Ja, marginalt stabil, sagde hun, eller imaginary.
Men man kunne man ikke også bare sige det meget simpelt?
Den andre, der er stabil. Nå, okay.
Jeg tror bare, at jeg marginalt.
Men vi tager chancen. Det er stabilt.
Er det kun en dag? Ja, kun en dag fra 8 til 18, hvor jeg forstår. Jeg ved, det var det 27, men nu er jeg ikke sikker på, hvad det er.
Ja, det er ikke sikkert. Der er der over mange gange.
Og så minus 1 på 2 år,
Speedchats.
Nu er jeg færdig.
Er det ikke mig? Jo, det er mig før jul.
Når står 56 timer, så kommer man tirsdag. Det er flot.
Jeg kan super
Hvad siger Martin?
Man ved,
Folk giver mange penge
nej,
for
jeg vil gerne. Det var bare det, var
Jeg har aldrig set nogen af de YouTubere, som laver sådan brugerplader og sælger dem for
Nogen synes, det lød nice, altså, man havde tid på at kun tage en skoledag og smide væk. Altså, man tager muligvis 3 skoledage og smide væk.
Så giver det fint, der laver sådan noget der. Har man 2 skoler, så er det så og så
det er godt blive meget mere om, at det kan det. Altså, der er
ja, men altså, man skal ikke overbrug alt det.
Kan du den første til at være student? Den første? Jeg fik den første til
Realdelen.
Okay, are you done?
Det mener hun ikke.
Okay, let's do it together then. So, we need to check if these systems are stable or not. And for checking their stability, we need to have the poles. And in order to have the poles, you have to find the transfer function first. So let's find the transfer function of this one. And because nothing is mentioned about the initial value, we assume all are 0. If we take the Laplace of this one and do the factorization, this is what we have. And from here, the transfer function would be 1 over s minus 1. Yes, please. If nothing is mentioned, it's always 0. But if you, in the description, you find that, for instance, y of 0 is equals to 2, then it's not 0 anymore. You have to use this new given value.
I just thought that for the LTI systems, it would always be 0.
Yeah, but as I said earlier, if nothing is there, like this one, we assume always all are 0. Now, here we need to find the poles. So I put the denominator equals to 0. So I have P1 as plus 1. And here, again, the real part of P1 is greater than 0. So we are in the right side of the plane. We are here. So based on this, we have on a stable system. Am I right? Okay.
That's me.
Now I want to show you just an example. Assume for now that x of t is u of t. So we have an input which is bounded. We know that y of s would be always the multiplication of transfer function by Laplace of input. So if I do 1 over s minus 1 multiplied by Laplace of u of t, which is 1 over s, then I have the output in frequency domain. Then, if you do partial fraction expansion and everything, the y of t in time would be this one. Now let's look at this and see if it's bounded or not. Actually, if I do the plot here, the input is bounded. So the input is the orange one. And if you do the plot for the output, you can see it's not bounded. It goes forever upward. So it's not bounded, and it confirms what we obtained earlier. And here I just wanted to show you, in exam you don't need to do this, what's called the bluish, greenish color line, just to show you that what we obtain by using this technique always will confirm the orange, not orange, bluish color one. Okay, any question here? Now let's move to the other one. Here the only difference is that instead of minus I have plus. So again, we do the same approach. And then we obtain the transfer function. The transfer function will be 1 over s plus in this case. Because here, instead of minus, I have a plus, so it will become plus here as well. So I have one pole at -1, and the real part of P1 is smaller than 0. So we are in the left side, so we have a stable system. Actually, let me go here. If, again, if you do this bluish color for this example, you can see the output would be bounded between 0 and 1 as well. So it confirms the stability. And for the third one, we follow the same steps. We do the LaPlace, so it will become and from here the transfer function would be, which this can be written as s minus 1 times s plus 1. So here we have two poles, P1 at +1 and P2 at -1. Here the real part of P1 is greater than 0. Here the real part of P2 is smaller than 0. But we know that based on what I have told you, as far as only one of the poles are on the right, like the one we have here, then the system becomes unstable. And I have a solution here as well. So this is how we use the poles to check the stability of the system. Any question? Yes, please.
How exactly did you, if you wanted to get a graphical view of how of it is unstable or not, how did that exactly work?
You should do the plot all in Maple or MATLAB, but in this course we don't need to do that.
Okay.
We just use the poles to identify if the system is stable or not. Actually, I think it's the last slide. I have an example of actual exam, so you can see how I usually ask for this stuff. It's I think the last one. Am I right? I think it's the last one. No, it's this one. This is the actual exam question for previous semester. Yes, please.
If you have two positive poles and one negative pole, will it be stable or unstable?
As I said, as far as only one of them. So if one is unstable, but even if it becomes more than one, for instance, we have another pole, let's call P3, which is also greater than 0, it is again unstable. So for stability, everything should be here. But if 1 is here, 2 is here, or 10 is here, it doesn't make any difference. The system is unstable anyway. Yes, please?
Instead of doing the partial fraction, couldn't you just take the denominator and put it to the equal 0 and take take the
that.
power of a half?
Yeah, you can do that. But here I just wanted to show you that.
Okay. And if you had
Because if you use this and put it in Maple equals to 0, automatically you have these numbers without going here, and it's okay.
Yeah, and if you had +1 instead of 1, you would have an imaginary number, of course, afterwards.
Yeah, then you have maybe complex or imaginary.
And then it would be marginal stable, or?
It depends. If all are, it's a very good question. Let me show you then. If you have a complex number, for instance, if it's 2 here, you have a complex number here, or here, for instance. This is unstable. Because, why again? Because the real part is greater than 0, and it's in the right side of the plane. So it's unstable. However, if you have only imaginary number, not complex number, so you are maybe here, or maybe down here as well.
Marginally.
It's marginally, because the real part is not greater or smaller. Then it will become marginal.
Which we also could say it was unstable, right?
Yeah.
So,
Depending
both
on which
right.
definition, yeah.
All right.
Was it a question?
Yeah, I just want to give the roots. If you put it to +1, the roots would be a 1i and -1i.
Yes, or j. Then if it's for instance -j or +j, then you have here and here, which is marginally then.
Yeah.
Yeah. Any other question? Now let's have 15 minutes break.